Hi there, and welcome to our APSC 100-103 Qset Microreactor proposal presentation conducted by Group 707F.
The Martian environment is just the different soil samples and results from geological analysis, what chemical tests, spectroscopy, and environmental sensors will determine if the environment is capable of supporting life. Our goal is to examine different soil samples and then determine if the soil samples or the Martian environment is capable of supporting life. Certain problems are present within the design, such as getting enough soil into the cuvettes and accurately turning the carousel. Aspects that were looked at for the first issue were optimizing sieving and what material will be used for transport tubing. With the carousel, it was crucial that it could be viewable through a PyCam. There were certain specifications we were required to follow in order to help us complete our objective, which is to complete the analysis within a 15-minute time frame. The microreactor should be a maximum weight of 5 kilograms, and this is including mass from the water and chemicals used. The microreactor should hold no more than 50 milliliters of liquid, and the complete design should fit within a 30 by 30 by 30 centimeter cube. Any electrical components must be 5 or 12 volts. Experiments must be viable between temperatures of negative 10 degrees Celsius and 40 degrees Celsius in standard atmospheric pressure. All chemicals must be safe, legal, and capable of transport into the United States. No excess heat must be used as a catalyst for the experiment, and design should not exceed $90.
The design process taken by our team was first conducted by analyzing the various requirements and constraints that our client had presented for the project. We then looked at the key issues presented by the client, which were to prevent chemical contamination and to prevent chemical leaks. We then had a brainstorming session where we came to some conceptual designs, all surrounding sort of a cubic feature for the microreactor. After each design was made, we developed an evaluation matrix and weighted each solution with various criteria to decide which solution should be our final proposal for the client. Such criteria included the chemical test times, the size, the weight, budget, time commitment, the complexity of the solution to the chemical leaks, and the solution to the cross-contamination problem. We found that design C was the best option and then tested it through modeling and analysis. Design choices made for the final design were motivated by quantifiable functional specification and analysis of how the task being carried out by or around the microreactor might affect it, which was done before the design process began.
Various factors were taken into consideration during the design process and implementation of this project. Technical factors such as the manufacturing of the project parts was noticed, where we decided to use a TPU filament for most of the microreactor, a cheap, strong, and very durable material that could be 3D printed on Mars, rather than spend extra money for transportation from Earth to Mars. Financial factors were taken into consideration with the $90 budget provided by the client.
We realized that chemicals would have costed a large amount, but if provided from the university's chemistry department and other electric devices were provided, then we would save a lot of money for the transportation. The money saved also reduces the amount of fossil fuels burned for the rocket that transports the various materials from Earth to Mars. Environmental factors are already taken into consideration as the lid is removable and users can remove the said samples within seconds and dispose of them within seconds.
The Queen Space Engineering team requested that a microreactor system is built to be fitted atop the rover that was being constructed for the university rover competition. The solution that we found solved the problems that Qset encountered with the current design while sticking to the given requirements and constraints with the microreactor. The solution that was proposed attempts to decrease the chance that any mechanical error will occur by minimizing the number of moving parts in the microreactor. The proposed design also tries to solve the two most important issues in the current Qset design, being chemical leaks as well as cross-contamination. The proposed solution uses one-way rubber valves incorporated in each test tube with the chemical indicators and water already being preloaded. This will help to mitigate any chances of chemical leakage within the system, as well as limiting the need to insert chemical indicators as well as water in the test tubes. Each test tube will be placed at different distances from the center of the carousel. The test tubes will have their own designated entrance points that contain different samples, which will help decrease the chances of any cross-contamination. In order to reduce chemical reaction time, the design aspects can be taken advantage of by the analysis algorithm to conduct reactions and analyze them in an asynchronous manner due to the opaque nature of the microreactor's walls. An interior lighting system will be placed, which consists of various LEDs around the camera, which will help ensure the visibility of the test tubes and the resulting color of the reactions.
There are three main objectives that we can use as a group to evaluate how we did on this project. The first one is providing solutions to the various issues faced by Qset when coming up with their microreactor design. These issues involve the chemical leakage within the microreactor, as well as cross-contamination between soil samples. The second objective that we had was to have our microreactor meet certain performance metrics in terms of its structural integrity, and this was done by modeling it in SolidWorks and testing it using load tests and drop tests, the load test with 50 kilograms and the drop test from half a meter, as that is about the maximum it would have to withstand on the actual rover. The third thing is to meet all the constraints. These constraints include the size constraint of 30 by 30 by 30 centimeters, as well as the weight constraint of 5 kilograms, and the budget constraint of $90, and the time constraint of a 15-minute window in order for all the chemical tests to occur. All of these objectives were met as we provided solutions for all the issues, or the major issues that were faced. The microreactor passed all of the performance tests in SolidWorks, showing that at least as we modeled it, it can withstand the loads and the drops that it should. And we did all of this within the constraints of the project, which is the most important part, as without the constraints, the project would have been a failure.
This design delivers on the quantifiable functional specifications that were set out at the beginning of the design process. There is, however, room for improvement. In particular, there are two cases for the improvement of this design. We learned in the design process that through FEA, we could achieve major weight optimizations without compromising structural integrity. We believe there is still opportunity to further reduce the weight of the microreactor using FEA. Validation is also a critical component at almost every step of the design process. This became more apparent as the semester and the project progressed. Validation of results, of mechanical design choices and experimental design choices is the basis for justifying the work being done. This design could be improved through more validation in the form of real-world testing and through validation in the early stages of the design process.
Since no physical prototype is being built, nothing will be shipped or delivered to the Qset team. However, if the Qset team is interested in building our prototype, most of our items are fairly common, so should be able to be ordered online and shipped to a desired location if these materials are not already available at Queen's. For the disposal of our prototype, sustainability was a big thing, so everything should be able to be repurposed. So all the 3D printed frame, the carousel, and the test tubes are all able to be recycled so that they can be used to build a new project. As well, the chemicals that we have, the ninhydrin and the Sudan-4, are fairly safe chemicals and can just be stored in a sealed container as long as they're kept away from immense heat until we are able to properly dispose of them. As well, our electrical components are motor and Raspberry Pi camera. These items are fairly versatile and can be used in a variety of different projects, so when our item is being disposed of, these can be taken off of it and be used in a new project. This makes our prototype fairly sustainable and easy to dispose of.
Thank you for listening to our presentation. If you have any questions, please direct it to the upcoming question period. Thank you.